Well, I made it. I'm here. It's great to be here, seeing you in person. I met some of you in office hours. You had no idea I can walk, right? It's great to see you. And this class is actually first time I taught 3 or 4 years ago. It was here. It was a big class, graduate course. And I was terrified. I was a postdoc, just joined Michigan. And students were super nice. All things considered, they were really supportive of me, and here I am. So it's good to be in this class again. And 3 years after that, when last year, I had a GSI called Peter. We did, I think, a lot of new things. The course was really good. And then our rating went down. And students weren't happy. Then I asked Peter what happened. We did a lot of new work. I thought they like it. COVID is not my fault. And he said that there weren't as many jokes as last year. He took the class with you guys. And I said, but they weren't funny. He said, still, having them better than not having them. So I'm going to make my jokes throughout the course, if any. I won't be surprised if you don't laugh. So I'm fine with that, and I just move on. And the first one is not a joke. I realized Draw PDF is not free. And if it's not free, you cannot have this type of paper. I figured it last night, but I figured I can download Jesse's note and continue on that. I can do that. I try to stick to the same style because I know you guys are used to it, so I do my best to follow the same ideas of how to present the material. Okay, so we'll start from the concept of local and global minima. So I think this part was covered. I just review. A function, you know what's a function now? A graph of a function is a set of points that you see on this plot, all the red dots. This is called the graph of a function. Or the set of x and f of x. Okay? We put all of these into a set, and this is the graph of the function. Now, if you draw any line from any 2 points on the graph, for example, here and here, and if you connect these 2 points, if it doesn't go through the graph, the function is convex. If you cut the line anywhere, it's not convex, like here. This function is not convex because the line is going through the function, and the graph of the function is above the line. Or sometimes you read it's called concave up and concave down. But it's more common to say convex, and concave is when it makes a cave. It's the other way, right? This is concave. Okay, so this extends to any set. If you have a set, a circle, for example, is convex because you can just draw a line between any 2 points and the circle, and it doesn't cut the circle. So this is the notion of convexity. Another way to think about it is that if I compute the gradient of this line at any point, the tangent line, the function is always above it. There's no place for a convex function that you can draw the tangent and the function is not above that line. Here you see that it's easily, the condition is easily violated here. So this is not convex again. This is a second way to think about it, which is more useful in optimization because we use gradient to do root finding and solve an optimization problem. And this, Jesse told you, this is a whole field. You can have a book and course, undergraduate level, graduate level on convex analysis, convex optimization. The consequence of that for us is that if the function is convex, there is a unique minimum. If we find any local minimum, it doesn't have to be unique because your function can be like this, right? But they're equivalent. All of them are, all the points here, all of them are our global minimum because the function takes the same value. It's a straight line. Again, in the calculus course, you see that we can take the second order derivative, and then if it's positive, we say this is a minimum. If it's negative, we say it's a maximum. And if the function is convex, you can prove it, then the solution is unique. That translates to safety sometimes. That you can solve a problem for a robot globally optimal. That means this is the best we get. And there's no local minimum. That means that there's no danger of the perception goes wrong and the robot misinterpret the environment and take actions that are not reasonably optimal. So that was, I have a picture for this. I will add. I learned this from Jesse. I had no idea you can do this. You need to click. Okay. Now you should feel good because this figure is from my slides from mobile robotics. It's a graduate level course. So we're talking about the same stuff. You remember this, Trippy? A little? Okay, let me see. Now, what I want you to be comfortable with is this idea of having a line segment, like the red line, and it's not possible to write in the image. This idea of having parameters between 0 and 1, theta, times x1 plus 1 minus theta times x2. So this is really interpolating between x1 and x2. It forms a line segment. When theta is 0, we get x1, right? When it's 1, we get x2. When it's 1, we get x1. So you can move anywhere in this line, red line, by picking a value for theta. And you might come across this. I remember we used to do this to read numbers from thermodynamics tables. You find a number that is not in the table and you need to interpolate. I guess it's better to do it by computer, but we had to do it by hand. So this is just really interpolating. Now, if you pass this line segment into the function, of course, it's going to take a value in the graph of the function, this line here. However, if you interpolate the function values in the graph of the function, that line will be above the graph of the function. And that's the line we saw there. So this means a function or a set is convex when you take any 2 points and make a linear approximation of that area by a line segment, then that remains above the function graph or inside the set. Then that's the notion of convexity. So you can use these symbols to make it more formal, like this. And you have this inequality. That interpolated value, if you evaluate the function at any point, it's always less than or equal to interpolating the function values. This is really what we talked here, is just with symbols and math. I think Jesse added that to the notebook, but that chapter is not complete yet. All right, so we're going to move to the next topic, and just going to look at my notes. We need to talk about hyperplanes for several reasons. That will add enough background for this course to be accepted as prerequisite for machine learning and computer vision, which is reasonable. They use it a lot, but that also shows the importance of the topic because it has a lot of applications. For example, if you want to we're going to talk about hyperplanes. I'm going to add a figure. We might not reach that far today, but this will motivate us to carry on the discussion. And this is really just one example, but it's a very relatable example from machine learning. Okay. All right, imagine I have two categories, cats and dogs. Here are red circles and blue crosses. +1, -1. These are labels, whatever you want to label, right? Inside, outside, whatever. It's a binary classification problem. You want to categorize a bunch of objects, points here, into two categories, two classes. And this is called a classification problem because the output is discrete. You learned regression. When we solve a regression problem, the output is, in project 2, the output is continuous. In machine learning, that's called regression, which is coming from linear algebra. The case when the outputs are discrete, that's called classification. That's also very important. For example, image classification. That was the breakthrough 2008. Between 8 and 12, Google trained a neural network on ImageNet data set. They could classify 1,000 classes of image. You can classify cats' videos on YouTube, for example. Make a playlist, right? Recommend it to people. That's all it's doing. But 1,000 classes. Here, it starts with two classes problem. It all started with this problem. How can we do that? Now, this is a really simple case. We see that visually we can separate two classes. And there's a line that goes through it. Okay, this is a good observation. How can we generalize this? Of course, not everything is going to be on a 2D with 2D points. We need a model that we can generalize it to higher dimensions. The coordinates of plane that we see, x1, x2, we can think about them as features. Just like regression, when you had the phi row that you just create features, we can have hundreds of them. We want to use them to still classify objects into two categories. One example, you work at Google and they tell you, make something that we can detect spams in the email, right? Every email that is coming to your inbox, you need a model to label it whether it's a spam or not. If it's a spam, it goes to the spam folder. If it's not, it remains in the inbox or whatever other rules that you have, then it will be applied to that. Okay, that's somebody did it in Google, a group of engineers probably. This is the same problem. It's a binary classification problem. But you shouldn't use this because then you get a lot of spams. Probably that's how it was in the beginning. I don't know if you guys remember, but I remember there was a time that it wasn't that good. You could get a lot of filters. So it's a model, and your model is not perfect, and you can improve it over time. So the notion to generalize point, line, plane, to higher dimensions, when we have a lot more features, x1, x2, x3, x100, is hyperplane. Now, you already know that it doesn't have to be linear, just like your regression. You can have nonlinear basis, just like Gaussian basis. And that's where it becomes really powerful, because you can have a curved, it's still a linear problem in the sense of linear algebra, but your basis is nonlinear, and you can, for example, separate objects in circular way or literally curvy way. And that was a breakthrough 20 years ago, support vector machine, kernel methods in machine learning. Okay, so this is one motivation. There are other problems as well. But I guess this is enough story to know that this is an important problem. Let's look into the math now. Do you have any questions so far? Just feel free to interrupt. Okay, you don't have to wait until I'm done. Now, I spent the weekend to come up with a way that is fun to explain what is a line. The best way, I liked it. There are many ways. There are lots of, if you can Google up, of course, there are thousands of tutorials. I didn't like any of them. And the one that I liked suddenly came to me is that use the dot product. It makes everything terribly simple. You know dot product? A reminder? I think this is the notation we use, but this is equally valid as well. This was A transpose B, or B transpose A, and it was A1, B1 plus all the way to AN and BN. These are just some vectors. And the dot product is just a component-wise multiplication and then adding all the terms. Okay, so now when the dot product of two vectors is maximized, I don't see the chat. Do you look at the chat? Let me know if there's any question. Jesse's here. Did we cover, Jesse, when the dot product is maximized and minimized? It's gone. No? Okay, so this is very important. The dot product is maximized when two vectors are parallel or aligned. So if I have A, then I have B, then A dot B is maximized. However, if there is an angle between two vectors, if I have, again, A, and then if B is like this, let's call this case 1, this is case 2. A times A dot B, I'm just going to use this notation. It's a little non-standard, but I guess you understand what I'm saying. This is bigger than, A and B are the same vectors. Same vectors. Okay, so this is as good as it gets. When they're aligned, they're in complete agreement. The dot product is maximized. And when they're not, well, it depends on the angle. When it's minimized. Now, the definition of dot product says that it must be greater than or equal to 0. So it cannot be negative, at least in this context. Okay, so then we say, and you are able to compute the angle between two vectors. Just a side note. Cosine of the angle is A dot B divided by norm of A times norm of B. This is not good. Try again using a thinner pen. And then you take the arc cosine. It will tell you the angle. Now, without going through too much trouble why it's like this, this is the formula. And it's a good, these questions are great for Piazza, right? So why this formula is true, or how can we prove it? Then we can go into details. So A dot B must be positive. The norm is positive. So the right-hand side is always positive. And the cosine of an angle that is always, when the cosine of something is positive, the angle must be between 0 and 90 degrees. Okay? Because if we pass 90 degrees, it's going to become negative, right? And then the maximum angle can be from 0 to 180. Because otherwise, if it's shorter, we go from the other side. There's no reason we go from the longer direction. That's when an airplane is moving and you see in the map, you think it's taking the longer distance, right? What the hell is going on? You see the map that from America, I'm going to go, I don't know, this is America, and this is UK. It's a very abstract idea of America for me. Before I come to America, this is how I imagined it, and this was UK, equally abstract. I was here in Australia, still abstract. Because it's too far. This is, just call it OZ. Now, you want to fly to UK, you say, okay, why the plane doesn't take straight line to go to UK? Instead, it's just doing this. Do you know why? Trippy?
Because it's a sphere.
Right. Excellent. So because it's a sphere, right? So some people don't believe that Earth is not flat. So for the sake of conversation, let's assume the Earth is not flat. Okay, it's a sphere. If we believe that, then if you want to move in a sphere, well, there is no straight line, right? You need to follow the curvature of the sphere. Things are a little complicated. If you want to move from one point to another point, you cannot just draw a line. And that's called the generalization of straight lines on curved spaces. It's called geodesic. So this is A geodesic is the shortest path on the sphere. It's just our brain can't handle that. Oh, it's not a straight line. Or maybe because that's how we were trained. Like we start from Euclidean geometry, but that's just one type of geometry. It doesn't have to be like that. That's just the first geometry we discovered, and then we generalized that. So it is the shortest path. So what I was talking about is that if this is A and this is B, we don't take this, we take the shortest path, right? So we tend to take the one that is smaller. All right, so and then the dot product will be actually this one, because we take the angle between the extension of that vector. Because vector by definition is just a direction, right? It's not a specific point in the space. So we just extend that line and we see when they collide. Okay. So it can be negative, right? The dot product can be negative? It can, right? It's the norms. I made a terrible mistake. So this can be negative, right? Jess is not telling me you're wrong. So this can be negative, actually. But anyway, this is the angle. So it can be negative. So the angle is, going back to the conversation, is between 0 and 180, okay? So it's not going to be 240, 360. Okay, so now when A dot B is minimized, when do you think it's minimized? Exactly. When A is perpendicular to B, the angle is 90 degrees. Which we will get 0, right? Because the only way that cosine of theta can be, the angle can be 90 degrees is when its cosine is 0, okay? So the dot product should give us 0. So it's minimized, it's just, so the angle is minimized. That's the correct way to say it, because let me correct this. So what I wrote was completely wrong last night. The angle maybe you can do some examples in presentation with computing the angles, just a bunch of vectors, right? This whole thing might become a little complicated. Okay, so A and B is vectors. All right, so if that's the case, now we're ready to define this notion for the Euclidean geometry. Again, this is going back, the reason I had this discussion, because hyperplane in different contexts can have different meanings. You can have projective geometry. Cameras are projective spaces. You can have, and that comes down to, you can have a triangle that is a straight line. You can have a fat triangle. you can have a thin triangle like this. The first one is Euclidean geometry. The middle one is Riemannian geometry. That's that sphere, for example. And the third one is hyperbolic geometry. This is the geometry we use in physics. They use it to model a space-time. It's called Minkowski space. One extra dimension is time. It has negative signature. 3 dimensions is space. They model the universe using this. And the universe, as we move, like in any direction, it has this negative curvature and has this expansion. But we're here. And you're going to be here for a long time, unless you take maybe advanced differential geometry course. I never heard of the other two in my undergrad or master's degree. I think maybe these days you might have some related topics about them in differential geometry courses. Okay, so let's define line. Pick a vector, let's say 2D space. I don't have a paid version, so I don't think I can draw frames like Jesse's doing. I'm working with a minimal version of Draw PDF.
I think it still has it.
It has it? Okay. This is better. It's like a craft beer and a bottled beer. Jess is giving you the bottled beer. This is craft beer. It has imperfection, but that makes it unique. Let's get a vector like A. We draw our vectors from the origin for now. Let's talk about set of all points such that A dot X equals 0. Pick any other vector, pick any points such as X, right? And then draw a vector from the origin to that point. Basically, if X is a point, and then X minus 0 is a vectorized version of that in this Euclidean space, which is X again, right? So the difference between 2 points is a vector, and one of them can be 0. So we can always convert a point to a vector in Euclidean space from the origin to that point. Now, the dot product of any X that you can pick, collect all of them, that produces 0. We just talked about it. The only way it gets 0 is that if the angle is 90 degrees. So what does it mean? Can somebody formalize it a little bit? A rough conversation. So we're going to make a bigger, oh, it's not straight. The sad part is that there is a guide. I can see the line. All right, I have my vector A. What are all the vectors that will produce dot product of 0? I want to draw those points and then create a set out of it and then give it a name, which is a line. We're going to talk about it. So if there's any point, right, by definition, if I can do this, and if the angle is 90 degrees, that's valid, right? If there's any other point here, x2, that's also okay. Here, it's okay. There's an infinite number of points. And all of them, if you connect them, it forms a line. Because it's a real number, we can just have any 2 points and as close as you want. You can go this direction too. So then we created a line. This is a geometric definition of a line. If we write it using the set notation, our line is well, this is 2D line. Well, in 2D, it's a line. You can have a 3D line too, but we want to talk about the notion of hyperplane. So in 2D, I guess we need to define A such that A dot x equals 0, right? You could write it different ways. This is one way, seems correct as far as my imagination goes. This defines a line. You, of course, learned it to be like this. Y equals mx plus b. And m was the slope and b was the intercept. Then how are we going to connect these two? It's important to connect them, because if they are not consistent, one of them is wrong, right? If they are correct both, we should be able to relate them. But that's not a problem. That's easy to show. Because, well, remember, A is just A1 and A2 in this case. And X is X1 and X2. A dot X equals A1 X1 plus A2 X2 equals to 0. Can I write it like this? X2 equals minus A1 over A2. X1, of course, A2 must be non-zero. Otherwise, the formula breaks down. Now, this form is called regressor form. You've done it in your assignment.
The question is, what about the lines parallel to the one we have?
Well, then they will have another A that is orthogonal, right? So it was completely arbitrary. I picked A to be any vector and then define all the points that meets that condition, right?
I think if it has to be parallel, then it should pass through the origin.
Yeah. Now, that question is valid, that if I have a line, then what's A? Yes, we can go backward to. But the direction that I came is that I have a vector, normal vector, A, and then I want to define the line. So we could go the other way. Because from the way I'm explaining it, you are already convinced that A is the normal vector of the line. It is orthogonal to the line. That will come handy. Okay, so, well, what if I define M to be whatever is A1 divided by A2, right? And then, of course, X2 equals M X1. Well, that's all good. There's no B. This is our line. it goes through the origin, it includes the origin, 0, is this a subspace? Is this a subspace? What was the subspace? We refer to the definition. The subspace must include the origin. Well, it does. When x1 is 0, the other one is 0. And the second condition was that any linear combinations of, this is a set of elements, points, that any linear combination of them is also in that set. Meaning it's closed under linear combinations. And it is. You remember from that convex set discussion that pick 2 points, interpolate a line, using that formula, pick 2 points on the line, well, it is a line, you can just move. So you will never leave the line. So if you pick any 2 points on the line, you're always in the line. Any linear combinations of 2 points on the line will be a point on the line. So the answer is yes. And yep, continue this part of the discussion on Piazza maybe. This is good practice. So it's a subspace, which an important notion here is that this is called a linear subspace. Linear fixes the origin. It includes the origin and fixes it. It keeps the origin. So this is a linear subspace. Now we want to talk about affine subspace. Sometimes it's called linear variety or linear manifold. Linear because it's flat, in this case, for manifold. Manifold is just any set surface in Euclidean space, here line, or in 3D, any plane or surface, that's a manifold. A surface in a Euclidean space, it's usually if you have a 3D space, your surface is 2D, right? It's because if you live on that surface like a sphere, that's 1 dimension less. And that's a manifold. A very loose definition. You can formalize it as well. So affine subspace or linear variety is when we take this set L, and then we say it's affine variety, let's call it M, is when you pick an element like V, a vector like V, and add it to L. What happens? So L is a line, V is just a 2D vector. And it means, this notation means that take that V and add it to every single point in the set L. So what happens, you get whatever, based on what's the value of V, right? You get many variations of this. Now they're not going through the origin because we added V to every element of the line at the origin when the line passes through the origin. When it's 0, now it's V. And that was the line y-intercept, if you remember, because now it does not go through the origin. So it's not a subspace or linear subspace, it's an affine subspace or linear variety. And this is really what in general we expected to see. A line can be anywhere. The ones that go through the origin are more special. Okay, so Now, if that's the case, then how can we formalize our previous discussion? Now, if you remember, I said take any vector A, start from the origin. Now, I'm going to tell you, pick any point, x0 and A, and then repeat the same process. I knew I'm going to get COVID if I come to the lecture. It's too late. I'm going to continue. At least finishing this lecture. It's not. I've been just coughing. Safe. I know it. Unrelated to COVID. Okay, so if I pick any point here, right? It's going to go through the origin again. Let's pick a point here, x0, a vector A, right? Apply the same definition. Now, if I pick any x, to make it a vector, I need to subtract x0. Previously, it was the origin because it was 0. Now, I can generalize my definition to a dot x minus x0 to be 0, right? Because my starting point is not the origin now. It's x0. And then I get a line like this, which is a dot x equals a dot x0. Now remember, x is an arbitrary point. x0 is a specific point. It has a value. And then let's define this to be a constant like d. Just whatever it is, a dot x0 is just a scalar number. D is a real number. So I can write a1 x1 plus a2 x2 equals d. Now x2 is again, A2 is non-zero. And by the way, A cannot be 0 vector. That you can imagine already. At least one entry of A must be non-zero. Otherwise, there is no, well, normal vector. Now, we can define M to be same as the previous case, and B to be there you go. We got our line. So the line that we know is an affine subspace, linear variety of all the lines that go through the origin. This formalizes and generalizes. And what we like to do, we like to extend this to we should stop. Okay. So we're going to extend this to 3D. That's very short. You can do it next time. That will give us a plane. If you add one extra dimension, think about it. It will give us plane. And then you go to Rn, that's hyperplane. But the dot product, whatever I'm talking about, is exactly the same. You just have A3, X3, A4, X4, right? AN, XN. That's it. And that will be hyperplane. So we're going to cover that quickly next time. And then once we have that, we can talk about quadratic programming and now how to formulate our classification to solve using QP. And then when we can do that, we have great insight what's going on and how to solve a QP. Those are two valuable skills you can carry over any project in engineering with you. Okay? So see you on Wednesday.